Hello, and welcome back to Stat 3050 at the University of Wyoming. We're online, and we are having a good time. Oh my lord, we're having a good time. Okay, so in the last couple of videos, I was talking about how to interpret change in regression models when one of the predictor or the outcome is log transformed. So in one of the videos, we talked about having a log transformed y, and in the other one, we talked about having a log transform x. And it turns out that when we log transform both of them, that kind of combines the terminology from both, sort of the interpretation from both. And well, let me show you. So let's say that we have some regression equation, something that has both the predictor and the outcome log transformed. And so I'm just going to kind of make this up as I go. We'll say 5.1, that's going to be our slope, and then we'll say 2.1, and then times the log of x times the log of x. So you can see now that both of these are log transformed. There must have been some kind of curvature or some unequal scatter in the residual plots that warranted this kind of transformation. And now we want to figure out, well, when x changes, how does y change? What's the sort of relationship between that? And right now, we can't do all too much. We cannot do all too much with this, keeping it in the log term. So what we want to do is we want to put it in some function of x, y as some function of x in this case. So what we want to do is put y as some function of x. Y as some function of x here. So how do we do that? Well, let's try to get these logs out of here. Well, how do we do that? Well, just a great question, So we know that an exponential and a log, they'll cancel out pretty nicely. And since we did it over here to the left side, we need to do it to the right side as well. Okay. And it would be helpful now, maybe pause the video and go find some old, pre-cal notes or some algebra notes, or go online and look up kind of a sheet of all of the log rules here, because we're going to be using a lot of them. Okay, so I'll give you just a second to go do that. Okay, a second has passed. Here we go. So we know that this e and this log, they'll cancel out pretty nicely. So that just equals y. And then we know since these are being added together within the exponential, that can be split apart and multiplied. So we'll say exp, or e to the 5.1, times e to the 2.1 times the log of y. And that's all within the exponential here, Okay, so if you recall, or if you have it up, there's a log rule, where when we have some kind of situation like this, where we have some value being multiplied by the log of just an x, well, then we can actually just move this 2.1 into the exponent of the x. So that looks something like this. In the terms, at least in the terms that we're using right now, this exp, that would look like this. exp times the log of x, and I'm going to use a caret here just so I don't have to write tiny, 2.1, and that's what it looks like now. And you'll notice that, hey, these are now next to each other, they can cancel out, so that's great. So we'll rewrite this as exp, or e to the 5.1, and then just x to the 2.1, and look at that, bingo, we have got a new regression equation in the original units, in this y and x. There's no more logs, there's really only one exponent here, and it's all good, so we're all set. So what we want to figure out is that when x changes by some amount, how does y change? What's the relationship? What's the interpretation of this model? Well, just a great question. It turns out that when we do this x plus 1 kind of business to some exponent, right, to some power, that is kind of difficult to work with. And so just like last time, instead of doing it this incremental change, instead of looking at it as an incremental change, we'll look at it as some percent change. And let's say that we want to see when x increases by 5%, we want to see how does y change? How does y change? Well, what we do, just like always, is we'll make a little page break here, and then we'll say y equals e to the 5.1, e to the 5.1. And then, instead of having just x to the 2.1, we'll put in parentheses here, 1.05 times x to the 2.1. 2.1 there. And we're just saying 1.05 because we want to include this as a growth, right? If we just left it as 0.05, right? If we left it as 0.05, that would be saying something along the lines of a 95% decrease, which we don't want, So we're just adding this 1.0 here, this 1 to the 0.05, just to denote that it is, in fact, increasing, right? Okay, so what do? Well, if you remember from algebra, or whenever, we'll know that when an exponent, when a term that looks like this has an exponent on the outside, has some power on the outside, that can be applied to both of the terms. So we'll write it like this. So you'll notice that this is our original equation that we saw up here. So that's nice. And then we get some value here, 1.05 to the 2.1. So I'm going to bring this into R. I'm just going to real quick plug this in. And it turns out that this value here is about 1.11. It's pretty sweet, right? Pretty sweet. So we can say that, hey, this is actually being multiplied. This is being multiplied into our regression equation. So that's saying that for every 5% increase in x, let me write that up here too, 5% increase in x, y increases by this 11%. 11%. So we'll say, we can write it out, a 5% increase in x results in an 11% increase in y. Well, so I don't want to have to go out and do this math every single time, right? We can start to notice that this 5.1, this is our original intercept, right? This beta naught. And then this 2.1 was our slope, right? And then we've got some value here, p, we'll say percentage p, and then again our slope, right? Our slope. So we can write this out as the following. If x increases by some percentage, and we call that p, some percentage p, y will also increase by the following. And this gets a little hairy, but we can kind of see this up above too. We'll see that it increases by 1 minus, okay, here we go, big bracket, and then 1 plus p over 100, end parenthesis, to the beta 1, to the slope, close that bracket, and then multiply that by 100. And that gets us some percentage increase. And that's pretty much it, right? Seems a little hairy, seems a little tricky, right? And it can get pretty complicated the more predictors that we're adding. But for right now, let's just worry about it on the simple linear regression context. And we see that it really boils down to this thing, right? To this fairly simple equation. So if you wanted to, and of course you're not required to, but if you wanted to, and of course you're not required, if you wanted to do an interpretation of our regression equation and both terms are logged, then you would just plug in some percentage that you choose, that you're interested in, that is relevant to the research question or whatever. Plug that in for p, look at your slope, and just do this equation here. And then you're set, and then you get some percentage of y. Okay, so again, a lot of math, nothing to be too hung up on. If you have any questions, just let me know. You can find a lot of this online as well. Again, review those log rules and exponential rules just so we can kind of get familiar with that, and so you're familiar with that as time goes on. And that's it for this. not too much math elsewhere in this course, so don't worry about it. Don't worry about it. But of course, questions, email me, whatever, Skype, it all works. And I will see you next time.